Okay, hi everyone. Welcome back to our next webinar. Today we're going to be talking about how engines work. I'm James.
I'm Diego.
And let's talk about engines.
All right.
All right. Now, quick reminder for those of you returning and for those of you who are just tuning in for the first time, if you have any questions or anything that you'd like to add to the conversation, or sometimes we'll throw out a question to you guys, you can put those into the question and answer, the Q&A feature below, and we'll see that. All right.
All right.
Take it away, Diego.
So today I'm really excited about this topic. It's called How Engines Work. How Engines Work. And this is a course offered by Heron. And for parents out there, if you're watching, it has a study guide, so you can learn how engines work with your kid step by step. If you've ever been mystified by the engine, I've studied lots of engines before. I was reviewing the course, and there's just so much data in here, so much information, and just stuff that you can do at home. So let's get into it.
Okay.
All right. And feel free to answer questions. I got James here. He'll help me field questions. He'll help me get your questions answered. One of the first things is to talk about is a piston. Okay. And a piston is basically this. We can show this.
All right, let's do this.
Let's slide the motor this way.
This is heavy.
We have a motor in here because that's what we do. And this is in our science lab all the time, and kids can take it apart when they're on the course. And
I'm going to angle the camera down so we can see that a bit better.
Sure. So this is a Kubota. I forget the name.
All right.
Do you want to pull up our slideshow? We have the actual motorcycle that this was taken from. It was a Japanese company. You got the, we got the tilting down. Good.
Yep. There we go.
All right.
Here we go. All right. So there's a diagram of a.
Hey.
Yeah. Go ahead.
Yeah. Actually, let's go back a slide, or no, maybe forward a slide. Okay, there we go. So this is a Hadoka Trail Bikes. And this was a Japanese motorcycle, and there's a lot of cool things about it. This is called a two-stroke engine. So go ahead and back to the camera. This part removes here, and we have a spark plug on top. This is what explodes the gas, and the spark plug comes through the bottom. So if you were to look inside this engine while it was firing, that's where you would see a little spark coming up. And this, right away, you can tell that this engine is an air-cooled engine. And you can tell it because the way these slots are cut into the metal, or when it's cast, and that just allows air to go by and keep it cold. With engines, if you can keep the inside hot and the outside cold, the engine works better. You get more, they call it efficiency. But all this means is that the engine is able to get more miles per gallon.
Because if it got too hot,
it wouldn't be good. If it gets too hot, it starts melting, things break down. But you want it really hot and really cold. That difference is what makes engines more efficient. Especially a combustion engines. So we can take this part off, and this slides on two posts, and you're looking inside an engine. This is the cylinder here, and so this is inside the cylinder. Gas and explosive gas exhaust is what we call it. So gas comes in, exhaust goes out, and you can see some of those portholes in there. This right here is a piston, and you can move that piston up and down, and as the gas explodes, boom, and then you get these different cycles, these different parts of the engine. You get the combustion stroke. So you have two strokes happening, and they do all these different things. We'll get into that in just a second. But it makes this piston in here, and this is the piston. It makes this piston go up and down. Okay, so this sits on there. So this thing is made to handle a bunch of explosions. When you hear a gas engine going down the street, you're just hearing explosion after explosion. And some of the favorite engine noise that people like are the Ferraris, because they have that Ferrari sound. And those have 12 cylinders in a lot of those engines.
So one of those 12-cylinder Ferrari engines would have 12 of these guys. and they're just all going kind of taking their turns.
Right, right. And so that as there's a rod in here, and it's this rod. Let's see, yeah, we can see it pretty good there. This rod that the piston is connected to, that rod is going around a shaft in here, and that's what gives you power. That shaft is connected to the tire, and then that's what makes the vehicle go down the road. With this, you can see how there's if you look at it from the side here, let me turn it around here. If you look at it from the side here, you can see all these moving parts. And what happens when you have that many moving parts operating really fast, you're going to produce a lot of heat. And so these gas engines, they're about, a good engine is about 20% efficient. So anywhere 10 to 20% efficient. What that means is that the energy that's in the gas, they can only convert 10 or 20% of that energy into power to go down the road.
So meaning the other 80 to 90% of the energy that exists within that gasoline that it's burning is essentially just kind of wasted.
Yeah, you're wasting all that
put
heat.
off into the atmosphere.
You're wasting all that heat.
Okay.
It's going into friction. It's going into wearing parts and giving you a bigger build, so you have more repairs and stuff. So people who know how to repair gasoline engines, there's always work, right? There's always work. They can't make, right now in the United States, they can't keep enough people employed on how to work on engines and stuff. So mechanics are always going to be
really important.
Yeah.
Yep.
Yeah. Okay. So that is a little bit about the piston.
Good. We had a couple people
Sure.
asking how big is this engine? What's the area of this engine? This motor.
The size, I don't think I got the size on this.
Those are really good
It's
questions.
that big. So they measure engines by how much they displace. So this may be 400 cc engine, something like that. Yeah.
Nalia, thank you for the question. I'm sorry we don't know the answer to that one. This engine itself hasn't been on a bike in a long time.
Yeah.
This one lives in our science lab here at the Delphian school, so that when you're studying something, engines or anything, it's really important to have the thing available to look at. If you're studying about history, you want to find some photos or videos or paintings of what it actually looked like. Try to, you dress up in costume, you recreate certain things so that it's not just words on a page, it's an actual thing in the world. History, it can be a little bit more difficult to get the thing in front of you because you have to recreate it. Engines, if you're studying about engines and you can like take one apart and look at it and move the pieces, it's really important and it really helps. So
Yeah.
hopefully this is helping you.
Yeah, definitely. So another thing, another way to measure engines is horsepower. So I have some stats here. 1 horsepower is enough to lift 550 pounds, 1 foot per second.
Okay.
So 550 pounds, 1 foot per second.
Let's see what that looks like. All right.
That's roughly, so to give you a visualization of that, that's enough power to take a person up a flight of stairs. So roughly, if you've ever ran up about 10, 15 steps in a second, that's about 1 horsepower. Right. Here's a visualization.
Yeah. Good. So that block is 550 pounds. That's a lot of cheese. I'm just assuming that's a block of cheese. And that motor is connected to it there. And it took 1 second to lift those 550 pounds of, I assume, cheese by 1 foot.
Yeah.
All right.
There you go. So let's go to the slide now, and we're going to talk about the different cycles on this engine. So we just saw the piston. We saw the cooling,
exact same thing I just left.
We saw the cooling fins, all these things. We're going to get in this diagram with this engine.
There we go.
This is the one we have on the table is a 2-stroke. The one in this diagram is a 4-stroke, but they work very much the same. So the first is the intake stroke.
Good. Before we jump into that, Eli asked a question I want to answer really quick. He asked, are you going to have another one of these next week? Eli, thank you. Today we're discussing engines. tomorrow morning, same time, 9 o'clock Oregon time, we're going to be talking about weather, which I'm really excited to talk about. And then next week, I forget which 2 days, but Diego and I are going to team up again. And for 2 days, we're going to talk about space. We are so excited to talk to you about space. This is not something that you need to convince us to do. We will talk about space to you whether you ask us to or not. So I really hope that all of you are able to join us tomorrow for weather and for our 2 classes next week for space. Okay. You were going to talk about the 4 cycles of
the
this.
4 cycles. So you have this diagram up on how engines work. The first one is the intake. And that's where this piston, when this piston is, it's at the very top and it starts going down. And what happens is it'll suck the fuel and gas in, or the oxygen and fuel in. So that's the intake part of the cycle. Then the next one is when it starts to compress, it goes up and it squeezes the gas.
Compress means to push closer together.
Yeah, and we're going to actually do a demonstration here of this. We're going to see a little mini explosion in a clear cylinder that we have.
So at the bottom, it's now pulled in the air and a puff of gas, right?
And
like
it all
spray.
That's right.
And it's closed, and then it kind of closes on the top, right?
Right.
And then as it comes back up, it can't go anywhere. The air and the gas can't go anywhere. It just gets pressed together.
Yeah. And are they able to see that in the big camera?
Let's see. Good. Thank you. Good point.
Okay.
Let me pop out here real quick.
Okay.
There we go. Okay. So it's at the bottom.
There we go.
And you've got air and you've got.
And remember, this thing is sitting on top of it,
Mm-hmm.
which this has a bunch of holes for the oxygen and fuel to come in.
So then once that's in, as it starts to come up, the air and the gas, they're stuck in there. They can't go anywhere. So it's not being pushed out. It's just being pushed together.
Yeah.
Okay.
Yeah. So then that would be the compression. And then we get to the power. And the power, we have the spark plug that's sitting on top of this part here. And you can see the spark plug inside there. A little spark ignites just like a barbecuer, and you get an explosion. Boom. And so
we can see that in the third frame here.
Yeah. And so that will drive the piston down. And then we get into the power stroke and then the exhaust stroke. So as it goes down, that's the power stroke. And when it goes back up, it's pushing all those burnt gases outside. Yeah. So it exits this, and this one, you can tell by these, after you studied a little bit about engines, your exhaust will be on the bottom. So this bottom part right here is the exhaust, and then this is the air intake.
Okay.
All right.
All right. So let's walk through that real quick.
Mhm.
I'll be the engine, and you describe to me what's happening. So we'll start at the top here, right?
Okay.
So part 1 is it goes down.
So that's creating a vacuum, and so that'll suck in oxygen and fuel.
All right, and then it gets pushed up.
That's the compression. So so we went to the intake, now we're on compression, squeezing down that gas.
And then
ignition, boom, we get power. So the power blows that up and sends the piston down, which turns the arm and gives the motorcycle power.
And then when it comes back up,
we're hitting exhaust. And then the cycle starts over and over again.
So as it's going like this.
There you go. And it's building up friction, and the whole engine's getting hot. And you're going down the road. Okay.
That's pretty much, I mean, it doesn't sound as cool as a Harley Davidson, but
That's it.
Not without the explosion and
everything else on the engines, all the wires and things like that, just aid to make this process better, to make it more efficient. I brought in a couple sensors. These are sensors that we have in our lab. So when students are measuring different things, this is an oxygen sensor. Now the ones that go inside your engine, they help detect how much oxygen you have in there. And so the wire,
because you need oxygen to burn stuff.
That's right.
Yeah.
And there's items in your engine that talk to each other all around a little computer, and that computer makes decisions. They're preset decisions that, okay, if there's this much oxygen, let's set the timing like this. And so it's getting like information from these oxygen sensors. So this is what an oxygen sensor looks like. On the inside, there's just a little place for the gas to go through, and they're just little electrical signals that come back to the main engine.
Yeah. A few questions for you. Shanna asks, how does it make the spark? How does the spark plug make the spark?
Okay. So to generate a spark, you need electricity. So initially, your energy is stored in a battery. That's why all cars that are made now are battery started. A long time ago, when cars first started, they didn't have great batteries that would get the car going, and so they had a crank. So in the front of the
You might have
Model
seen this
Ts,
in an old movie.
yeah. When you see it in the old movies and they're getting their car going, they have a big crank, and that's how they would generate the electricity to get the first spark going.
Yeah, or if it was a propeller plane, you would see them, they'd have to spin the propeller, and that would get that first bit going.
Yeah, they didn't have starters the way they do now.
Right. Cassidy asks, what causes the piston to go down in the first place? And that's a great follow-up to what we were just talking about.
Yeah. Oh, and we didn't even take this part of this totally apart. Let me pull this over. There's more parts to see. Thank you. I almost forgot to mention that. That's why what I love about our courses, because sometimes teachers just forget to say like a piece of information. So if you never heard a piece of information, then you have this hole in your education. That's what I love about these courses, is it's step by step, so you get all the data. So if you have to miss a day of school, you don't miss anything. You pick up where you left off in that step.
That's great.
Yeah. And so this, I almost forgot to mention it, is the flywheel. So let's turn this around here. This is a flywheel. And a flywheel, it's a big, super piece of chunky metal. And what it does is it keeps the motion going. It keeps the momentum going. And so if I spin this, as if I do that without damaging that. It's
a little loose, but that's okay.
If I kept it on track and I gave it a good spin, this engine would keep going through its cycles because of the flywheel. The flywheel is just, it has momentum.
Mm-hmm.
And momentum is just the ability to stay in motion. Like if you were to throw a big heavy ball, that ball would just keep going, right? It has a quality we call momentum. And a flywheel has momentum. It keeps the cycle going, so that way it doesn't sputter out. So when just as important as all these parts is the flywheel, because if you don't keep that cycle going, it would just die out. It would just be one explosion.
It captures some of that energy and it uses it to create the next cycle to create more energy. But at the beginning, you need to, the flywheel is not already moving when your engine is off. So you need to add power to it. So you're going to, when you turn the key or press the button, your car or your bike or plane or whatever is going to draw energy from that battery to create that first bit of power to create the first movements in the engine. And once that's going, then it's running by itself.
Yeah. Some motorcycles too, they have kickstarters. And so the person has to stand up and then crank down to get that engine going.
Yep.
As motorcycles are more pricey, they're able to just start it with an electric push start.
Yep. All right. And we're being asked, and all this is happening very quickly, right? Very, very quickly.
Yeah.
What we just showed here, that 1, 2, 3, 4, that creates one pop sound. And when you hear an engine going and you hear, or like each of those putts, that's 4 of these cycles. 1, 2, 3, 4. That's one putt. So I can't spin this with my hands fast enough to go putt, 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 putt.
If this is going full speed, it would just tear up your hands.
And then, one of the dials that you see on a car, it shows like revolutions per minute.
Yeah.
Right. That RPM, you might have heard, revolutions per minute. And when my, Prius is just kind of sitting there, not going anywhere, it's probably had like what, like 1,000 revolutions per minute or something like that.
Yeah.
So 1,000 RPM, 1,000 times in 1 minute. This thing going.
Yeah, and cars will run 2,000-3,000 RPMs
Mhm.
up to 9,000 RPMs. So being able to talk to that, to being able for the engine to find out what's going on inside the engine. Here's another sensor that we have. This is one that we use in the lab, but cars will have this kind of thing. This is a gas pressure sensor. So this, you put it in a bottle and you can get a reading on a computer of how much pressure is there. And so you can see how people are amazing and they think of all kinds of things. They're like, well, we could probably make this go faster if we add a sensor. If we knew this, then we could get this time. Sensors.
There's over 100 years of amazing ideas from really creative, intelligent people to make engines better and better and better. Kai says, after you use the battery to make the first spark that powered it, it also makes energy for itself to make more again, right?
That's
yes,
right.
Exactly.
Yeah, it recharges the battery.
Right.
So then the battery always has electrical potential, electrical energy ready there to keep it rolling, to power the lights inside the car, your stereo, all these things.
Excellent. And Lorna asks, how many engines can be made in 1 hour? Great question. And it depends on the factory. It depends on the place that's making them. I suppose if you had a big enough factory, you could make dozens of engines per hour. If it was just me and Diego sitting here, or like sitting in a tool shop, it would probably take us several days at least to make one engine. Yeah. Right
now, the electric cars are in such demand that they can't make them fast enough. They're setting up these giant, they're called gigafactories, and they can't make enough engines fast enough to get electric cars to people. So just amazing. There's a lot of things going on in the automotive industry.
All right.
Let's talk about diesel engines.
Okay.
All right. So diesel, I got a demonstration for this, so we can take this.
We can slide that out of the way. That's heavy.
Yeah.
It's heavier than it looks. I don't know if you heard that, but it was clunk.
Yeah. So this right here is a cylinder. This is kind of how a diesel cylinder would work. You have a see-through cylinder here. So I'm hoping that the camera will be able to pick it up, but we're going to show compression. Now, when you have enough compression, you can make things explode. Diesel doesn't use a spark plug like the gasoline engine. Diesel, what happens is there's so much compression on the cylinder that it squeezes the gas so hard that eventually it combusts it and we get a little explosion here.
It just squeezes it so tight that it just explodes all by itself.
Right. And so a diesel engine would work like this. They have really big compression ratios, is what that's called. And all that is just how much air is squeezed. So diesel has to squeeze a lot of air. So diesel engines are usually really heavy. They're a lot heavier than gas engines. So we can take a little, I don't know if you can see that. That's a little piece of cotton.
It's a little cotton ball, yeah.
Yeah. So this is the fuel, right? So this is going to be our fuel. So I'm going to get some of this and put it inside the cylinder.
Yeah, we'll move it. Oh, there we go. Okay.
And so I'm going to put our fuel inside the cylinder. And with the liquid fuel, cars are able to just do this really fast. Oh, there we go.
So right now, you can't really see this on the camera, so I'm going to illustrate a little bit what's happening. We've got the fuel's kind of in there like that. It's fluffed up a little bit.
Yeah, that's just cotton. And the reason we use cotton is because it has a lot of surface area. And what that means is just oxygen can get around the cotton and we can get ignition a little faster. This is a little tricky to do, so I'm hoping we can get it the first try.
Okay, good. So as you're screwing that on, it makes it airtight.
It makes it airtight.
Air cannot go out or in. All that's in there is the air that's in there now.
Yeah.
Okay.
And I'm going to give it a shove, and we'll see if we can get a little spark. And here we go. 3, 2, 1. I don't think I got it.
Did we get it? I don't think so. All right.
3, 2, 1. Try it again. I had a little bit of problems with this in the lab, but 3, 2, 1. I got it working a couple times. but it's try it again.
Okay, yeah. So what's going on here is he's got it sealed there, and he's pushing that down. He's doing it with his hand, but in a diesel engine, that the power of the engine is pushing that down for you.
Yeah, the flywheel keeps the momentum going.
And as it goes down, that same amount of fuel in there, in this case it's cotton, in a diesel engine it's the diesel fuel, gets compressed all together into a much smaller space. When you press stuff together like that, it gets really hot.
Okay, ready?
It should go pop.
3, 2, 1.
Yes. I really hope that you guys could see that there. We had a little flash.
Yeah, hopefully you guys were watching that, but we had a flash. But what we did is we combusted that cotton. And when we take this off, we'll have a bunch of charred black cotton. And you can see the remnants of it.
Yep.
Yeah. And so that was compression. That was compression.
All right. A few questions here. So one good question. What is the difference between diesel and gasoline?
So diesel is, diesel doesn't vaporize as much. If you've ever been around a gas station, you'll see the gas fumes are kind of in the air. When you go
really
by
smell them.
Yeah. When you go by diesel, it's not as volatile as what we say. It's not escaping into the air.
Okay.
And so it's more like it's just more liquidy.
Okay.
Yeah, it doesn't vaporize as much.
So they're both types of fuel, but I know from not me doing it, but I've heard plenty of stories. If you put diesel fuel in a gasoline engine, it doesn't work.
Right.
If you put gasoline fuel in a diesel engine, it doesn't work.
Yeah. They're just two different types of fuel sources. So all the machinery to handle them are just different setups.
Yep.
Both are fuel, both have lots of energy. Diesel engines they're a little more efficient than engines, but this course gets all into the nuts and bolts of what are the benefits to gas versus diesel.
Yeah. So thank you, Lorna, for that question. And Ariana asks, so then how can the four wheels go with only one engine? Good question.
Yeah. So transmissions, that's a whole subject.
Transmit means to take something from one place and send it to another place.
That's right. Transmission is just, it's how the power gets there. Yeah.
That I think it goes into more detail on that on the course, but basically there's rods and poles and all kinds of things connected to the engine. As the engine turns, that's too heavy for me to pick up right now. But as you saw things in the engine moving, that motion then gets kind of sent to different parts of the car. So
yeah. So to give you an idea, the compression is 16-to-1 for diesel, and gas is 8-to-1. So the gas in a diesel is getting squeezed down a lot more than a car engine.
Wow.
Yeah.
Okay.
And one thing we didn't talk about LeBron James.
I was wondering when you would bring up a professional basketball player while we talk about engines.
Yeah. LeBron James, if you don't know who he is, he's a really powerful basketball player.
And he has the best last name in the world, which I also think is a great first name.
Yeah, that's right. James Galunas. So LeBron James is capable at maximum output of 9,300 watts, which is equivalent to 12.47 horsepower. Now,
so LeBron James is 9,300
watts, which is the same as about 12.5 horsepower. So earlier we saw that diagram on what horsepower is. That was the ability to pick up 550 pounds in 1 second. So that 1 horsepower, he's 12 times that ability, right? So if you think of one example, an average NBA player can run across the court in 13 strides. LeBron James does it in about 8 or 9. So this guy is,
and he's traveling the whole way.
People could say whether he's the greatest basketball player of all time, but I don't think anybody would argue that he's not powerful.
Okay, good.
Yeah.
Fair. We were about to get into an argument about basketball.
He's
So
definitely-
is he as powerful as 12.5 horses?
Yeah, at his maximum output. Now he can't sustain that. He can't sustain that for an hour or anything. But to give you an idea, it takes about 2,000, 3,000 watts to run a house, right? So at his maximum output, he can roughly maintain 3 houses, you know, to kind of give you an idea. But that would be at total maximum output.
Right.
So
now this measurement here, the measurement of a horsepower, that's I'm sure that horses can put out more power than just that, but I think it's a useful way of measuring 1 ounce of one bit of energy, right?
yeah, yeah. And
Okay.
when you look at our course, the 550 pounds being lifted in 1 second, that is 1 horsepower, and that's about what a horse is capable of pulling. I don't know the historical, you know, if they put a horse and figured out how much he's capable of. I don't know that exactly, but that's what the data is on 550 pounds in 1 second.
Good.
What it takes to lift that.
Right.
All
Thank you,
right.
LeBron James.
Yeah. So to give you an idea, so more on this subject of horsepower, some of the diesel engines, so if you have a big electric engine, go ahead and pull up the other slide of one of our, this is one of the titans of locomotives, titans of the trains. And this train, yeah,
There we go.
this is a Russian train, is capable of 17,838 horsepower. This thing is amazing, over 17,000 pounds of horsepower. But the cool thing is that what generates this horsepower is the diesel engines, and but the force that they are generated with are electric engines. So most locomotives are powered by a diesel engine, and then that diesel energy is transferred to an electric engine.
Okay.
Which to me is just really impressive, and I'll tell you why in a bit.
Good. All right. So we've talked about gasoline engines. We've talked about diesel engines. This is your first mention of an electric engine.
Yeah.
Okay.
An electric engine. Yeah.
Good.
Yeah.
We'll talk about a little bit more of that.
Yeah.
soon.
Oh, yeah. I got some really cool demos. I'll give you a really quick, just for the camera if you're watching. Yeah.
Here, let me pull out here.
Okay.
What do we got there?
I'm just gonna give a flash, so stay tuned till the end.
Okay.
I'm just teasing you a little bit. There's more to learn about electric engines. So with steam engines, steam can expand over 1,000 times of its volume in water. So that's why steam is a great source of fuel. Well, not fuel, but an expansion mechanism for steam engines. So just how we have the gas expanding on a piston, steam engines perform in a similar way, but they can use any type of fuel, and that fuel makes the steam, the water heat up. And so when you have heat,
Do we have a slide of that in here?
I don't have a
Okay.
slide on that. Yeah. So
So let's say we have a pot of water. Do we have a blue marker? No, we don't. So this is water.
we have green, which is pond water.
Don't drink pond water. And you've got fire under here, and that boils the water.
Yes, this is great.
There we go. And we've got, so then that water boils, turns into steam. Can we see all that? Yep.
Uh-huh.
And it goes up here and it gets piped into the engine. This is our engine here. So instead of the gasoline exploding, getting sparked and exploding and pushing the piston down, we have this steam being pushed in there at super high pressure, and the steam being pushed in pushes that engine down, right?
That's right. Pushes
Okay.
a piston, and then that piston
Yeah.
can drive something. Now, the amazing thing about steam engines is what happens right here between the water and gas stage. That's where steam, just because of heat, expands 1,000 times. And James Watt, who was one of the first,
Great name.
yeah, get a theme here. One of the amazing things is that expansion.
Mhm.
And tapping into that, James Watt, if he was alive today, probably the steam engines he would be able to make, because now we have more efficient ways to carve aluminum and carve all these things out. At the time, he was working with pretty crude tools for making engines, but there's people that still use a lot of steam engines. The steam engines are just these super powerful, amazing horsepower engines that, you know, they still use them on like steamrollers. They're still using them because they can generate so much power to pave roads and things like that.
Yeah. Okay. Lorna asks, when and where was the first engine made? I don't know the answer to that question. That's a great question.
Yeah, that's in the book.
Is it?
Yeah, it's Otto. Let's see if I can get to it. It's right in the book.
How great is that?
Reading that. Yeah. Otto. I'm sure someone's going to pull it up on there. Throw it in. Yeah. The four-stroke cycle gasoline engine was invented by German inventor Nicholas A. Otto in 1876.
Okay. 1876. Lorna, thank you. All right. And then Ariana, with a follow-up to her earlier question, she was asking how does one engine send that energy to several wheels? And we described that there was the transmission and different pieces of the car that connect to send the power to different wheels. She asked, so then how about a four-wheel drive? Does that take two engines? No, what's going on with a four-wheel drive is the one engine, my car, like a Prius or a Camry or most cars that you're going to find on the road, there's power going to just two of the wheels, either the front two or the back two. A four-wheel drive, if you're going to take a Jeep and you're going off-road, instead of sending the energy just to two wheels, it's sending it to all four wheels. In a two-wheel car, only two of the wheels are being pushed by the engine. The other two wheels are just kind of rolling along with it. They're just getting pulled along. Like when I would pull my brother on a wagon or something like that.
Yeah. Let's get into jet engines. We're running out of time, and I would just there's so much stuff.
All right, we got 7 minutes left, and I want to talk about jets.
All right. So this is our jet engine. So what a jet engine does is air comes in. So this is something you would see on a commercial vehicle, but air comes in here. This fan pushes some of the air around the outside, so around this part right here, and helps cool the engine. But majority of it gets sent on the inside of this cone, and it compresses the air, so it's squeezing. So there it is again. It's that compression of gas that we take advantage of. And then right on this part that's red right here, we get an explosion. And so then the gas is compressed, and then it explodes violently, and then it gets sent out through the back of this. And this little piece right here, this nozzle is there to control that flow of air, to keep that air uniform. And so what happens is you're getting this thrust, and it pushes this forward. So explosion in here pushes this forward here. So everything, all these little fans, and then on the inside here, there's a bunch of blades, and all those little blades are just to squeeze the gas more and more. And so with our gasoline engine, all this compression, it's fighting parts. This doesn't fight parts. And that's why these jet engines are capable of super amounts of horsepower, because they're not fighting against itself. It's not producing.
It's not pushing like this.
Yeah. The only friction is just the turning friction. So you're able to there's a lot of really interesting things that jet engines are able to do. And so they're not practical on cars, although some people do put. We were at the what was it called, the air show?
Yeah, the Oregon International Air Show, and some brilliant person had attached two jet engines onto a fire truck. This man is my hero. and that thing got moving quick.
Yeah, very impressive.
Lorna asked, how big is a jet engine? It could be all different sizes.
Yeah, they make them this size. There's some really great YouTube videos of people making jet packs, and they'll have like 4 of these on their arm, and they're like flying around. Yeah.
Like Iron Man.
Yeah. So
or you can have it big enough to put on a jumbo jet, and 2 or 4 of them will take you across the Atlantic Ocean.
Yeah, so they're able to make them in a variety of sizes.
Yep. Noah asks, are there pistons in a jet engine?
No, that's a great question, and that's one of the reasons that the book gets into it and kind of talks about the advantages. But that's one of the advantages of a jet engine. There's no piston, so you're not having all these problems with cooling.
Right.
Yeah.
And right on the heels of that, Akanksha asks, what is friction again? Right. So take your hands, put them together, rub them, and they start to feel warm. That rubbing together is called friction. Friction creates heat. So with a piston engine, and it's constantly moving up and down, and it's moving, you know, if this is the side of the engine, this is the piston, and it's moving like that, it's going to create heat, especially because there's explosions happening every, you know, several times a second. With a jet, there's less friction. There's still some friction as it's turning around inside, but less extra heat is created that way.
All right, so let's get into our electric motors. So this is an electric motor that somebody would make in our lab. So we have electromagnet course. I don't know what the exact name of the course is, but
yes,
they end up making they make an engine, and this is one of like an example of an engine that kids would make. There's
see, I'm going to tilt that camera down a
Sure.
little bit more.
I can
cut off.
actually,
Oh yeah, okay,
yeah, I can
good.
just go like this.
I'll hold it for you.
There's all these coils here, so I have a great demo here. I have another great demo here, and this is an electromagnet. So an electromagnet, when you take a battery, so let me slide this out for just a second.
Okay.
This is called an electromagnet. And James, you're the switch guy.
All right.
Okay. And get this set up here. So this is a coil, insulated copper coil, and it's wound around this bolt. And what we can do is we can create a magnet. So you'll see that this thing is not magnetic. It's not.
If we scoot that a little bit back this way.
Yeah,
there we go.
This piece of metal down here is not magnetic. But when we run electricity through these copper cables, we can generate an electric field. So go ahead and throw that switch.
All right. The switch is connected.
See, make sure we're connected to all these other wires. I have a wire that's out somewhere. Oh, I see some power there.
There we go.
Okay, so go ahead and pull it up. It was just working. I swear. What the heck?
Well, if everything was connected and everything
we're getting
was
spark there,
and there was things properly running here, then we would have.
there it is.
It's magnetic.
Yeah,
there
so
we go.
Let go of the switch.
Boop.
Try it again.
On
Okay, off. There it goes.
and off and on and off.
Okay, so
do
you
this
saw,
all day.
Yeah. So what you're seeing is this thing is turning into a magnet on and off with the switch. Well, James is pretty fast, but with certain computers, with setting up timing, you're able to generate that. You're able to make that that switch on and off with this little part that's called the commutator. So that would be on this side. It's kind of hard to see in this diagram here, but basically with you're turning these things magnet, this is turning a magnet, then this is a magnet, then this is a magnet, and this is a magnet. And it's going on and off, and it drives this shaft. And so you end up getting an electric motor. So this is a very big, really, I would call it like a crude form of an electric motor, but it's a great learning tool that you can do on one of our courses that gets you understanding what an electric motor is. Once they're miniaturized, we can then take a motor like this, change your switch man again.
All right.
Wires turn off. So we have an electric motor here. This is just a battery. These are totally fun to play with at home. You can take apart toys, things like that. And
all right, so it's off, on, off, on, off. This red wire runs to here. Black wire runs to here. Yay.
yeah, And so we have an electric motor being turned on and off. So that big version that we just saw that was a big on the board, it's condensed into this little electric motor.
That's great.
And these electric motors can be turned into, yeah, cool you down.
Yep.
These, you can use them for fans, you can use them for cars. It's just a matter of making more and more batteries.
Now we are running out of time, so I wanted to answer a question.
Sure.
When we were talking about the jet engine, several very astute viewers noticed that there was a key point in our explanation of the jet engine that was missing. And that was the fuel. Like, where does the fuel come in?
Oh, okay, yeah.
Yes.
Yeah, piping. So we can pull that up real
We'll
quick.
pull this up again real quick. I'll hold that for you.
Yeah. So in this diagram here, you can see that this is where the fuel is injected. So in back of this engine, you would have fuel getting sent right here, right after. So the compression happens right here. Then the fuel is inserted here. So the fuel would just be coming in on a little pipe, and then it gets ignited, and then that gas gets blown up and it shoots out the back of this engine.
So just like with the other two fuel engines that we were talking about, the air gets compressed, the gas gets compressed and ignited, and then gets shot out the back.
Yep.
In the case of a jet engine, gets shot out the back and
Really fast. So
that
it's
propels you
a
forward.
lot of thrust.
Yes, thank you to the several people that pointed that out. All right. Chris asked, we're back to the electric motor here. So the number of times the wire is wound around it affect the magnet's power?
Yes. Yes. Actually, Tesla motors, so they have Model S's. If you want like one of the high-end ones, it's like the Model S 100D. The motors are hand wound because you can get robots to make these motors, and they can wind them, and they make a really good motor. Robots can make a really good electric motor, but it's interesting that they have to hire humans to make sure that each strand of wire is compressed into the smallest amount of space. And those motors on those top end Teslas are all hand wound.
I did not know that.
Yeah.
That's awesome. That's so cool.
Yeah.
All right. And Lorna asked, why copper? Why copper wire? It's a really good conductor.
It's a really good conductor.
Allowing electricity to run through it very, very easily.
Copper has some interesting properties, and you can get into the chemistry of that. But in a nutshell, copper is just a unique metal. There's a lot of things. You can use other metals, but copper is just the best one, and it's readily available. So that's to answer that question really quick. But it gets into some of the chemistry of where the electrons are and what they do.
Good. Well, we are at least 3 minutes over time, but I did not want to cut our viewers short. Was there any last thing that you wanted to talk about before we end off?
This is the world's first space car. So Elon Musk, we had a viewing party when the Falcon Heavy was launched, and it happened at the school. It was a super cool event, but they put this electric car, the full-size version, Elon's first model Roadster, Tesla Roadster, and they put it in the Falcon Heavy, and they launched it in roughly a Mars orbit. And so the first car that's flying in space is an electric car. I'm still like blown away by this feat.
Yeah. All right. So thank you so much for joining us today. After I end the broadcast here, I'm going to leave the Q&A up for a couple of minutes. So if you have any last questions, you can send them in and I can respond to that. Coming up next, I think 10:15 today, Robin's going to continue talking about American history. Diego and I are back tomorrow morning at 9 a.m. We're going to be talking about the weather. And again, next week, you'll see the schedule when we put it out, but there's going to be 2 days that we're talking about space.
Yeah.
And I think this Tesla Roadster is going to come back into the conversation.
Oh yeah, for sure.
All right. And one final thing, let me go to the final slide here on this slideshow. At heronbooks.com, where this course and many other courses are available, you can use the promo code Delphian30 to get 30% off of any product listed there.
Yeah, and today's course was how engines work. How engines work.
Good. All right. Thank you, everyone, for tuning in. We'll see you next time.